Hello everyone, and welcome to the next video in our GMAT Ninja Quant series. Today's video we're going to take a close look at some number properties. Now, number properties is such a big topic that we've had to split it into two, so this is part one of the two-part series. First of all, we'll take a quick look at what we mean by number properties, because different people define it in different ways. When I talk about number properties, I'm thinking about things like lowest common multiple, greatest common factor, divisibility, finding factors of numbers or remainders, as well as some miscellaneous stuff like, is this an integer, or just odd or even questions that you might fit into algebra, but we've slotted under number properties. Now, as I said, we split this into two videos, and in today's one, if we're looking at the topics, really I'm going to be focusing today on lowest common multiple and greatest common factor and divisibility questions. But this split is less about the topics and more about how you approach the questions. We thought with number properties, it's almost like nailing jello to the wall sometimes. There are some things you can formalize, and today's video is going to be about formalizing the things you can formalize, maybe using some of this quasi-algebra that we'll take a look at later, whereas the next video is just really, you've got some jello, you've got a hammer, you've got some sharp nails, and you're just trying to find any pattern you can to nail that jello to the wall. So today's video is going to be a little bit more formal. There's going to be a few more methods, a bit more algebra. Next time, it's just going to be about spotting patterns. Now, in terms of the difficulty rating here, we're going to run the full length. We're going to start that with some basics. There'll be some nice, easy stuff to begin with. We'll ramp up as we go through the middle. And then just as a warning, the final question today is a real killer. You don't need to be getting this final question, even if you want something like a 49 or a 50. But it's just nice to see these things sometimes. So we're going to ramp the difficulty level right up as we get towards the end. Now, if you're asking me sort of who this video is for, we've got three ideas here. First of all, if you're getting lost in the word soup of number properties questions. Now, by word soup, I just mean you struggle to get things started. You don't really know what these words or phrases mean, and you struggle to turn the text into algebra. We'll take a look at that today. And then the next two bits are either if you feel you don't have a method, or if you've got a method but you don't really understand why it works. If you've just memorized a process and that's all you've got, then today we're going to dig into the background, into why these questions work or how to approach them and how to generalize that method across to other questions. So hopefully that gives you an idea of what we're going to take a look at today. Now, without any further ado, I will get the first question up on the screen. We'll give you a couple of minutes to take a look at it before we get back together to work through it together. All right, I will see you back here in a couple of minutes' time. Okay, if you've watched any of our other videos, you'll be used to this by now. If you need a little bit more time to work on this one, now's your chance to pause the video. We'll still be here when you finish your solution, but I'm going to take the question away now so we can take a closer look at it together. All right, so starting out with quite a word-based one, as we said at the beginning, part of this is about converting these questions from text into algebra. Part of the challenge is, what do you need to do? Now, if you see here, the main thing here is this middle sentence. If your alarm repeats every 12 minutes and your partner's alarm repeats every 18 minutes, at which of the following times could both your alarms go off? So we know that they both start at 6, then they're going to go off at different times, and we want to know the next time that they come back together and go off at the same time. In other words, this question's a lowest common multiple question. I want to know when my 12 and my 18, the multiples of 12 and the multiples of 18 will match. Now, just so that we can cover everything, I'm going to go through how to find the lowest common multiple. With number properties questions, there is often the formal way, the smart way, if you will, and then there's the stupid way. Sometimes the smart way is better, sometimes the stupid way is better. And we'll take a look at both of them here just so that you know what I mean by the smart way or the stupid way. Now, the smart way, or calling it the formal way, I'm going to take a look at the numbers 12 and 18. And your first job here is to break these down into their prime factors. I want to be able to split these numbers apart. And if you're struggling with number properties, one of the things you can do is get very good at breaking these numbers down. Being able to do this quickly is very helpful in these questions. So 12, we can say that's 2 times 2 times 3, or 2 squared times 3. And 18, doing something similar, is 2 times 3 times 3, or 2 times 3 squared. So then I'm going to take these numbers and line them up. Line these prime factorizations one on top of the other. And I want to know the lowest common multiple of them. Now, to find the lowest common multiple, I'm going to work my way along these lists, checking each number, each prime factor, and I'm going to take the highest power in each list. So I've got the 2's here. I've got 2. Well, that would be 2 to the power of 1, and I've got a 2 squared. The highest power of those 2 is going to be 2 squared, so I'll take that and put that in my lowest common multiple list. Then I've got the 3, that would be 3 to the power of 1, and 3 squared. Again, the highest power there would be the 3 squared, so I'll take that and put that in my list as well. Now, I know we don't have a 5, but just so we can see what would happen if there was a 5 in that list, there's a 5 in the top list and there is no 5 in the bottom list, then I would take the highest power, which is 5 to the power of 1 rather than 5 to the power of 0, and I would add that into my list as well. So if there is a 5 in one prime factorization but not in the other, and you want the lowest common multiple, we take the 5 with us. Then to find the lowest common multiple, we would just figure that out. I'm going to do that in a second. But for now, just for the sake of completeness, if I wanted to find the highest common factor, I'm going to work my way through the lists. I'm just going to do the opposite. This time I'm looking for the lowest power. So 2 squared and 2 to the power of 1. Well, I would take the 2 to the power of 1 and put that in my list. Same with the 3's. I've got a 3 to the power of 1 in the prime factorization of 12, 3 squared in the prime factorization of 18. For the lowest common multiple, I took the highest power. For the highest common factor, I'm going to take the lowest power. And so I'm going to take the 3. And now again, I know we don't have a 5 in these lists, but just for the sake of completeness, if excuse me, if there was a 5 in the prime factorization of the 12 and there was no 5 in the prime factorization of 18, I take the lowest power. In this case, I do not take the 5. So for the lowest common multiple, we take the highest power in each list. And for the lowest common multiple, we take the highest power. For the highest common factor, we take the lowest power in each list. Then it's a case we can just go and figure these out. 2 squared is 4, 3 squared is 9, 4 times 9 is 36, and that would give you the lowest common multiple of 12 and 18. For the highest common factor, 2 times 3 is obviously 6. Now, that might seem like overkill for numbers like 12 and 18 because there is this stupid method we talked about earlier. In this case, I'm just going to list some multiples. Well, I'm going to go up a little bit. There's some multiples of 12, and the list could go on. Now I'm going to take 18, and I'm going to start writing out multiples of 18 until I find a number that is in both lists. So the first number that's in both lists would give me the lowest common multiple here, in this case, 36. In some cases, just listing out numbers, that's going to be the quickest way to get there. In this case, yeah, that's probably the case. There are other times when these numbers are going to be much, much nastier, in which case breaking them down into the prime factorization and going through that process is going to be the best way to do it. Particularly if you end up with 3 numbers. If you have to find the lowest common multiple of 3 numbers, it's the same process. Line them up on top of each other, find the highest power of each prime factor, multiply those highest powers together. That'll give you the lowest common multiple. When you've got 3 numbers, doing it the formal way is probably the quick way. Now, to come back to this question, the lowest common multiple of 12 and 18 is going to be 36. So the alarm is going to go off every 36 minutes. Now, another part of the GMAT questions, you've got to be very careful with what the question's asking for, because if you thought the question said when's the next time the alarm would go off, well, if it went off at 6 and the next time they're both going to go off together is 36 minutes later, you'd think, well, the two alarms are going to have to go off at 6:36, but that's not any of our answer choices, and you start panicking. But this question doesn't ask when is the next time they'll both go off together. It just says, at which of the following times could they both go off together? So we know they're going to go off at 6, because that's what we're told in the question. The next time they're going to go off is at 6:36. That's not one of our answers. So we just need to keep adding 36 minutes onto this until we get something that appears in this list. So 6:36, yeah, adding 36 minutes onto that, well, 2 times 30, so it'll be 72 minutes. 72 minutes after they first went off together at 6 in the morning. 72 hour and 12 minutes. So we know the next time they're going to go off together is 7:12 a.m. Again, that's none of our answers, but at least we can begin to cross out. It's not A, B, or C, because they're not in our list of times when the two alarms will go off together. I'm going to add another 36 minutes on. So 12 plus 36 would give us 48. So these two alarms will go off together again at 7:48, and that would give us our answer of D for this question. Right, so this is a bit of an introduction. Lowest common multiple, greatest common factor. As I've said, there are two ways of doing this. There's many more ways of doing this, but these are the two that we normally show to the students. And there's the formal way, there's the stupid, just list the numbers out way. Both of them work, but they work better in different situations. And part of dealing with number properties is getting the experience of knowing which one works in different situations. All right, that's the end of the question one. I will get the next question up on the screen for you, and I'll see you back here in a couple of minutes' time. Okay, now's the chance to pause it if you need a little more time to look at this one. I'm going to take it away so that we can look at this one together. All right, looking at this question, I mean, it looks very simple. And some of you might have found it very simple. What we find with a question like this, though, is this one, or this sort of question, will trip up so many students, all the way up to people getting 50s, 51s, that sort of thing. This just setup will really stump some people. I think this is a little bit in how you approach it. One of the big things I want to get across here is please don't pick random numbers. Don't just start shouting numbers 1, 7, -12, a half, 2/3, 743, and just see what sticks. It might work. My question for people that try that in some of the tutoring classes is always, well, have you tried enough numbers? What about this one? What about this one? And we just keep going. It's very inefficient. And so this is one of those times where it's like, okay, we don't have a real formal method, but we're going to try and formalize this as much as we can. So data sufficiency question, I'm going to get this AD over BCE set up, ready to go so that I can use that as we go. And I'm going to look at first of all, take a look at the question. Is X an integer? I want to know if this number is a whole number or not. Can I tell? Now, first one, X squared over 2 is an integer. Well, from that, again, being very literal with it, I could say X squared over 2 is equal to, I'll just use some letter P, where P is an integer. Now I want to know about X, so I'm going to take this little equation and make X into the subject here. So X squared is equal to 2P, and X is equal to, well, we'll say plus or minus the square root of 2P. Now, the plus or minus isn't too important here. Negative numbers are still integers, but I'm really focusing on this square root of 2p bit. Could be an integer, maybe not. If we take this and look at it, if I chose p to be 8, then I've got the square root of 16, that would be 4. If I chose p to be 7, the square root of 14, definitely not an integer. Now, I know I said right up at the beginning of this question that don't choose numbers, but there's a very big difference between just picking numbers to throw at the question. As I said, 1, 17, 953, or what I've just done there, which is very clearly go, okay, 2 times 8 is 16. The square root of that will give me 4. That's an integer. That's one side of this. 2 times 7, not an integer when you take the square root of it. I'm choosing numbers to make a case rather than just picking numbers randomly to throw at the wall and see what sticks. So in this case, as we just said there, I could pick p to be an integer in such a way that I get a whole number out of this. Equally, I could pick p in such a way that I don't get a whole number out of this. So number 1 is not going to be sufficient, and I'll cross out a and d. Now we can do a similar thing with number 2. If the square root of x is some integer, again, I'll call that q. We know q is an integer because that's what this tells us. Well, then to get to x, I need to square both sides of this, and x is going to be q squared. Now, take an integer and square it, and you're going to get another integer. Doesn't matter what it is. You can try it out if you like. Pick some numbers, give it a test. If you square an integer, you're going to get another integer. So we can say that this is definitely sufficient. And we're going to go for b there. Now, as I say here, this looks very simple, but as I said, it trips up a huge number of people. The danger here is don't get tempted to just throw numbers at it and see what sticks. Think about what's going on. See if you can formalize this in some way. Come up with a bit of a method. Be very logical in what you do. If you need to choose numbers to prove your case, then be very specific about which numbers they are. Please don't just chuck numbers at them hoping something will make sense. All right. Now I will get this one out of the way, and we'll see you back here in a couple of minutes' time to look through the next question. Okay, if you need some more time to work on this one, now's the time to pause the video before I take this one away. All right, so this is the first question we're looking at where we're talking about divisibility. So we're going to pull this apart a little bit, take a look at the background, and then get into this question. I want to start by taking a look at what this question is actually asking for. Now, I know it says is x divisible by 405, but what does that really mean? Now, quick caveat before we jump into this one. The numbers here are probably a little bit bigger than you might see on the GMAT. So if you're struggling a little bit with the multiplication, that's okay. The ones on the real exam will probably be a bit nicer. But if you can get through this, great, you know you're really set up for the exam. Now, is x divisible by 405? Now, if x is divisible by 405, then we could say that x divided by 405 is equal to some integer. Could be 1, could be 2, could be 10, could be 375, could be anything. X divided by 405 will equal some integer. Now I could say that's 405 times some integer. And then just like we did with the first question, your job here is going to be to prime factorize this as quickly as you possibly can. Now, various ways of doing this that I'd say the first thing you can see that divides by would be 5. 405 is 5, well, 5 times 81 times a. Now 81 we can begin to split down. That's just powers of 3, and if you keep going, x is going to be 3 to the 4 times 5 times a. Now if x is divisible by 405, then in its prime factorization, it will have 3 to the 4 times 5 times something. Now, this could be, the a could be various other numbers, but at the very least, we're going to have a 3 to the 4 and a 5 in its prime factorization. So that's what the question's asking us to do. We've not even looked at 1 or 2 yet. We're still defining the question. But now that we've got this set up, we can go and take a look at the information we've been given. Now, first job, 27 is a factor of x. Now, in a very similar way, we can set that up and say, okay, if we know 27 is a factor of x, so we can say that x divided by 27 will equal b, some other integer. That must be a whole number, and that's going to be very important later. Well, that means x is 27 times b, and prime factorizing that, we can say x is 3 cubed times b. Now, I said to be certain of whether x is divisible by 405, I needed 3 to the 4 times 5 times something in its prime factorization. From piece of information number 1, I know I've got 3 cubed. I don't know what's in b. There could be another 3, there could be a 5, there could be various other things. I don't know. All I know is there is a 3 cubed, but that's not enough to say whether there's a 3 to the 4 and a 5 in it. So I'm going to cross a and d out. Now, piece of information number 2, very similar, but it's phrased in a different way. Now, if you've watched some of the other videos, like the percentages one, what we sometimes say is I want to rephrase the text that they've given us so that I can perform the same process every time and not get confused. In this case, I'm going to rephrase this from x is a multiple of 15 to 15 is a factor of x, because then I can do exactly the same thing that I did to piece of information number 1, and I know I'm following the same process every time. I'm never going to get confused because there's no variation here. And that works for, well, if it says here 27 is a factor of x, or x is a multiple of 15, or 64 is a divisor of x, or any of these variations on that text, if you always rephrase them into 15 is a factor of x, well, then you're never going to get confused by what happens next, or what, in this case, what goes on the top, what goes on the bottom. 15 is a factor of x, so 15 is the factor that goes on the bottom, the x goes on the top, and that will equal some other integer. Again, I'm just throwing letters here. We're working our way through the alphabet. I don't know what they are. Doesn't matter. All I know is c is some integer. Well, that tells me cross multiplying, x is 15 times c, or x is 3 times 5 times c. Now, on its own, it's clearly not enough. I know I've got a 3 in it, I know I've got a 5 in it, but I need a 3 to the 4 and a 5 in it. So piece of information number 2 does not give me enough. Now, C, we need to put them both together to check whether this is going to be C or E. And this is where you've got to be careful. A lot of people trip up by just going, right, I've got three threes here, I've got 1 3 there, that's 4 3s plus the 5, that's what I need, I'm done. Like, oh, we don't know that. What we need to do at this stage is find the lowest common multiple of these two numbers. So like we did before, I'm going to line them up one on top of the other, 3 times 5 times c, and 3 cubed times, I'll put the b over there. Now, taking the highest power, I'm going to work down the list again. I've got 3 to the power 1 and 3 to the power 3, so the highest power there would be 3 to the power 3. I've got a 5 and I've got nothing, so the highest power there would be having the 5 in that list. And then B and C, I don't know what's in there. I'm just going to put a different letter, D. Now, taking the lowest common multiple of those two, with them together, 27 is a factor of x, 15 is a factor of x, I know that the lowest common multiple of those two is going to be 3 cubed times 5 times something. Don't know what that something is, but that's enough. Now, that means that I know that x has 3 cubed in it, but I'm looking for 3 to the 4. Okay, the 5s are there, but I've not got enough 3s in my value of x from number 1 and number 2 to tell me for certain whether that's sufficient. So I can cross this one out, and the answer to this question is going to be E. So yeah, this is the bit in this where you've got to be careful. It's very tempting to just jump and say, well, I've got 4 3s and that's enough. Now, this would tell you what's that going to be, 27 times 5, so 135. 27 is a factor of 135, 15 is a factor of 135, but that's not enough to say that x is divisible by 435, because we just don't know from that. So with these, prime factorize everything you see. Again, 3 cubed, if that was enough, then we could say it's sufficient. If we know we've got 3 to the 4 and 5 in one of the pieces of information, that would be enough. But when you put them together, be careful. You're back to finding the lowest common multiple there. Don't get drawn into just adding the powers and running with it. All right, I will get the next question up on the screen, and we'll see you back here in a couple of minutes' time. Okay, now's the chance to pause the video if you want a little more time with this one. We're just taking it away so we can take a closer look at it. Now, this video is very similar to the last one, but I hope you spotted the differences there. The method we used for question 3 is not going to work here in question 4. There are some important differences here. First of all, I mean, we're not really asking about divisibility, but these 2 pieces of information you get in this question are very tempting to go do the same thing. Now, as we said in the last question, I would like to make sure I'm doing the same thing every time. So before we get into this question, I'm going to rewrite them in the same way. 7 is a divisor of x. Well, that's the same thing as saying that 7 is a factor of x. Now, I always want to say A is a factor of B whenever I'm doing this, so I'm doing the same thing. Number 2 is a bit more difficult to rewrite. If 42 is a multiple of x, then x is a factor of 42. And I'm back to doing the same thing. I'm performing the same process every time. Now, let's go back to the question and see what I'm being asked for here. So we know that x is a 2-digit positive odd integer, and I want to know what the value of x is. Okay, lots of information in the question there. I'm going to have to bear that in mind as we go through. First one, if 7 is a factor of x, then, as we just did in the last question, I can say x over 7 is equal to some integer. Or in other words, x is equal to 7 times a, so just x is something in the 7 times table. Now, yeah, we can just begin to list off some options here. There's your 7 times table for a few options. I know x is 2 digits, so it can't be 7. I know it's positive. Thankfully, that's all the things I've got listed here. And I know it's odd, so I'll get rid of 14, 28, 42, but that still leaves me with multiple options there, and I've only gone through the first few items of the 7 times table. Because I've got multiple options from the information there, I can't tell what x is. It's not sufficient to tell me, so I'm going to cross out A and D and move on to piece of information number 2. Now, if x is a factor of 42, Well, this is slightly different. Up till now, we've always had the number on the bottom and the unknown on the top. In this case, I could say 42 over x is equal to some integer. Okay, well, now I need to know what my options for x are. So basically, I need to know what the factors of 42 are. Now, again, this is one of those places where we can come up with some sort of method that means you don't miss anything. At this stage, normally when I'm in a session and I ask the student, what the factors of 42 are, they just start throwing stuff at me. 6, 21. I'm like, well, yes, those are all right. But how do you know you're not going to miss one when the pressure of the exam comes on? So the way I would approach this is to say, well, I want to add up to these numbers to multiply to 42, and I'm just going to start from 1, and I'm going to work my way up the numbers on this list. So 1, yep, that's a factor because 1 times 42 would give me 42. Next number 2, well, 2 times 21. Next number 3, 3 times 14 would give me 42. Next one I'd go to is 4. 4 doesn't divide 42, so we can ignore that. Same with 5, 6 times 7. And now, if I was to keep going down this list, the next number I would write would be 7. But that's already in this column, and so I'd just be working up the numbers I've already done. Now I know that these are all the factors of 42, and I haven't missed anything. So this is all I've got to work with. Now we can get back into the question. So I know x has got 2 digits in, so it's not 1, 2, 3, 6, or 7. I know it's positive. Again, not really too fussed here. All the numbers I've got here are positive. I know it's odd. Well, can't be 42 or 14. Well, that just leaves me with one number, which means that x must be 21. So number 2 by itself is sufficient to answer this question. And so my answer to this one is going to be B. All right, so in this question, as I said, in this video, we're going to formalize the things we can formalize. Finding factors of a number, if you can formalize it so that you know you can do it quickly, efficiently, and accurately without missing any options, that's going to help you in some of these number properties questions. So play around with this method. It can help you a lot in some of these problems. All right, I will get the next question up on the screen and we'll see you back here in a couple of minutes' time. Okay, now's your chance to pause it if you need a little more time on this one, because I'm going to take it away so that we can finish this one off together. So a lot of the stuff we've been doing in the last 2 questions should have helped here. A big part of this question is teasing apart that word soup, as we called it at the start of the video, to understand what information you've been given, how the 3 variables that we've got here fit together, what divides what, what's a factor of what, so that we can decide which of these options must be an integer. So to begin with, I'm going to ignore these options. I'm just going to focus on the text of the question so that we can pick apart what relates to what. Now, the first bit, P is a factor of Q. That's written in the way that I like. I can jump straight from that into a division sign. Because P is the factor, that goes on the bottom, Q goes on the top, and that will just equal some integer. Don't know what it is, don't particularly care. All I need to know is it's a whole number for this question. Now, the second one, P is a multiple of R. by the end of the video, you're probably going to get sick of me saying this. That's not in the way that I like it written. I'm going to rephrase that. If P is a multiple of R, then R is a factor of P. And so I can put R on the bottom of the fraction, P on the top, and that would equal some other whole number. Now, if R is a factor of P and P is a factor of Q, well, then we could say that R will also divide Q. And so I could say that Q over R, again, don't know what the number is, don't care, but it will equal some whole number. And that's going to be enough to get me through here. Now we just need to take a look at the questions one by one, the answer choices one by one, until we find one that must be an integer. There's no way out of it. Not could be, must be an integer. Now again, this is another question where you might be tempted to just chuck numbers at it until you find something that sticks. Again, that's a very inefficient way of doing it. You might be here for ages. It's probably far safer, far quicker in the long run to get comfortable with using the algebra so that you can be certain about what you're doing. Now I'm going to take these one by one, starting with A, alphabetically, no better reason, and say, well, okay, A is P plus Q over Q. Now in this way, I can split this fraction up into P over Q plus Q over Q. Now Q over Q, well, that would just be 1. They're going to cancel out, and so I'm going to have P over Q plus 1. Now P over Q, again, the question must be an integer. We know that P divides Q. P is a factor of Q. And in that case, P could be the same as Q. P could be Q because, as we've just found, any number divides itself. But we don't know that. P might be smaller than Q. It might be something else. P divided by Q, we can't guarantee that would be an integer. So our answer choice can't be A. We're going to do a similar thing with most of these. B, again, we can split that up into Q over R plus P over R. Well, in this case, we know that P over R, that's going to be some whole number. Q over R, that's going to be some whole number. 2 whole numbers added together, that's going to be a whole number. It's looking good. B's looking like my answer, but I'm going to keep going, check the rest just to be sure. C, again, split this up. Q over P plus R over P. Q over P, what we said right at the beginning, that's an integer, so that'll work. R over P, though. I know that R is a factor of P, and in the same way we did with A, it could end up being a whole number, but then again, it might not. And because the question is which one must be an integer, I can't tell. So the answer can't be C. I can't guarantee that's going to be an integer. Now D, slightly different. I've got PR over Q here. Now, it could be the case where, yeah, we get even though P and R are factors of Q, if we multiply them together, we get something that divides, that is divisible by Q. But I can't be sure. There's many, many, many situations where that is not the case. Again, think of an example. If R was 2, P was 10, and Q was 100. Okay, 20 divided by 100 is not going to be a whole number. Now, again, being very careful in how I do this here, I didn't just choose random numbers just to throw at the wall and see what sticks. I chose those to make a case. So there is a scenario where that would be a whole number. And R could be 2, P could be 100, and Q could be 100. 200 divided by 100 is 2. Equally, if R is 2, P is 10, Q is 100, 20 divided by 100 is not a whole number. So that one, we don't know whether it'll be a whole number, so our answer is not D. Now, E is slightly different because this time I cannot split up this fraction. This is something that lots of our students get tempted to do. Look over here. The 2 are on the numerator of the fraction on the top, and I've got 1 on the bottom. So I can split that up. These 2 fractions have a common denominator. In this case, the addition is on the bottom. I cannot split that up. Now, in the same way as we did with D, this one could be a whole number. I'm going to choose, let's say R is 2, P is 6. And this case, I'm going to have Q being 24. Well, in that case, 2 plus 6 on the bottom would be 8. 24 divided by 8 would be 3. That's a whole number. If I keep R as 2 and P as 6, but make Q 12, well, 2 divides 6, 6 divides 12, 2 divides 12. So all these 3 conditions are satisfied, but 2 plus 6 is 8, and 8 does not divide 12. We get 1.5. That would not be an integer. So again, E could be an integer, could not. Cross it out. As we said earlier, B is definitely the answer. Now, when you're doing this question yourself, you probably do not need to go all the way through there. When we got to B, we guaranteed that that had to be a whole number. And so at that stage, you might want to just take B and move on. If you want to be certain, yeah, we've gone through all the options. And as I've said down here, I haven't just randomly chosen the numbers. I've been very specific about which ones I've chosen to make a point. There's a big difference between those two. One of them makes a case, the other is just hugely inefficient in guessing. If you can be careful with the algebra, you can be much more certain about what you're doing. All right, that will be enough for that question. I will get the next one up on the screen for you just now, and I'll see you back here in a couple of minutes. Okay, pause it now if you need a little bit more time, because I'm going to take it away so that we can look at this one together. Now, while the difficulty of these questions begins to ramp up, I hope that the work we've been doing so far is helping you see where these questions are going. We're talking about very similar things as we go. Yeah, divisibility, prime factors, lowest common multiple, greatest common factor. And so, as the difficulty of these questions increases, I hope you're managing to see where these go. Now, in this case, we're asked, is n divisible by which of the following? And we're given this value for n, it's 19 factorial plus 26. Now, just to check, just in case you're not sure what's going on, what that exclamation mark means in this question, a factorial means that we multiply all the numbers from that start point down. For example, if we had 5 factorial, that would be 5 times 4 times 3 times 2 times 1. Or if there was 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1, all the way down to 1. Now we've got 19 factorial in this, so we've got plenty of numbers to play with. And I want to know, first of all, is n divisible by 13? Well, again, let's just take a step back for 5 seconds, say, what does it mean to be divisible by 13? Now, if there was a number x and it was divisible by 13, then x divided by 13 would give us, we're back to that integer, back to that whole number. Or in other words, x is 13 times that whole number. So if n, our number, if that's divisible by 13, then I will be able to say that n equals 13 times something in parentheses, and that would be enough. So I know that n is 19 factorial plus 26. Now 19 factorial, I'll write it over here so that we can use it. And so on. 19 factorial has a 13 in it, right? So there's no real nice way of writing this. So I'm going to say that's 13 times, I'm kind of just going to leave it there as 19 factorial without the 13 in it. And because I'm explaining it, hopefully you know where I'm going with this. And then we've got that plus 26 on the end. Well, that could be 13 times 2. So in other words, I could write n as 13 times 19 factorial without a 13 in it. Again, not algebra, but it's the GMAT. Nobody's ever going to see my working because I'm doing it on my whiteboard. I'm going to rub it out. That's enough. I know what I mean. Plus 2. So because I can write n as 13 times something, well, then I know that n is divisible by 13, and that's enough. Now, I've got to do the same thing for 2 and 3. For number 2, I would need to have 19 times something. Now, for the 19 factorial, that's easy. I could say that n is 19 times 18 factorial. But then I've got that plus 26 on the end. And there is no way of writing 26 as 19 times something. 26 is 2 times 13. There's no way of having 19 times something. So I can't split that up. I can't make n into 19 times one great big set of parentheses with all the stuff in it. And so for that reason, it's not number 2. Now, number 3, 26. Again, I'm looking for 26 times one great big long parentheses. Now, for the 26 at the end, that's obviously very easy. 26 times 1, that's great. But for the 19 factorial, that might be a little bit more difficult to see. I don't have a 26 in it. But what I do have is a 13 and a load of even numbers. I know I've got 2 at the end. Again, I've put ... there. I could keep going and say that that would have a 2 in it. So I could say that n is 26 times 19 factorial, well, without 13 and 2 in that list, plus 26 times 1. So n is 26 times 19 factorial without a 13 and a 2 in it, plus 1. So n is 26 times some great big long parentheses. That's enough to say n is divisible by 26. So 1 and 3 are, well, n is divisible by 13, 26. That means 1 and 3 work, which means that the answer here must be D. So yeah, in this question, we're playing on that idea of divisibility. What does it mean for one number to be divisible by another? And one way you can think about it is, okay, I could take that number, in this case n, and have it as 13 times everything else in parentheses. And if you can do that, n is definitely divisible by 13. And that'll help you solve some of these questions. All right, we're going to continue ramping the difficulty up as we go through the next few questions. We've got 3 more today. They're getting pretty tough as we go through, and remember that warning right at the start, the last one's an absolute killer. So let's build up to that one. I'll see you back here in a couple of minutes' time. Okay, you know the routine by now. Now's your chance to pause it if you need a little more time. I'm going to take the question away so that we can go through this solution. All right, so we're back to multiples factors, and we're back to playing around with the way these questions are phrased. Again, for now, I'm going to ignore the question. What I've got here, 6 to the power of x is a multiple of 144. So in the way we've done throughout the video, I rewrite that such that 144 is a factor of x. Now that gives me something I can work with. I know that the 144 is going to go on the bottom, 6 to the power of x is going to go on the top, and that's going to equal some whole number. Now we're going to have to keep that integer in mind because that's going to be very helpful later. The question is, what's the smallest integer x such that I get this? Now I've got this scenario. There's some way I'm going to be able to play around with it so that I know what the value of x is. Now when we get this set up, I'm going to prime factorize everything again. And this idea of prime factorization means that I'm going to know more about these numbers. Now on the top line, 6, well, I could say that that's 3 3 times 2. 144. Now that might take a little bit longer to split up. Feel free to take your time over this. We could say that's going to be 2 to the 4 times 3 squared. Now, yeah, don't worry. Set this video up so that we're not wasting your time. If you need a little bit more time to break that down, that's absolutely fine. But from here, what we can say is if I take the power across these two numbers, I'm going to have 2 to the x times 3 to the x on the top line, 2 to the 4 times 3 squared on the bottom line. And I want to know what the smallest value x can possibly be such that 144 is a factor of x. Now, the trap that you might fall into is saying, well, I want the smallest integer. 2 is the smallest integer, so I'm going to make x 2. Now, just to illustrate that scenario, if you made x 2, well, then we could say that's 2 squared times 3 squared over 2 to the 4 times 3 squared, and we can begin cancelling these things. 3 squareds will cancel. I'll end up with 2 squared over 2 to the 4, which is the same as 1 over 2 squared, or a quarter. But if you work your way back along these chain of equal sign all the way back to the beginning, we said that a had to be an integer. So we can't be left with 1 over something on the bottom. This is not an integer. So in other words, 2 can't be my answer here, so I can get rid of that one. What we need to be able to do is to cancel out everything and still be left with something on the top. And in that case, I've got two options. It's either going to be 2 or 4. I'm going to choose the bigger number, and we're going to go for 4 here. So that would leave us with 2 to the 4 over 3 to the 4 over 2 to the 4 times 3 squared. And if you cancelled out everything there, you'd be left with 3 squared, which is 9. Now this bit, the actual number that we get at the end of it, not that important, just to illustrate the point here. The point here is that the number I'm going to choose is going to be the bigger of the powers on the bottom because I want my answer at the end to be this integer. This bit at the start, again, seems pedantic, seems like I'm repeating myself again and again and again, but it becomes very important in some of these questions, and it leaves us with an answer of 4 here. All right, so as you can see, these ideas about rephrasing the question and divisibility and how you manage them come around again and again and again, and we're going to keep seeing them in the final 2 questions. Now I will get the penultimate question up on the screen, and I'll see you back here in a couple of minutes' time. Okay, now's your chance to pause it if you need a little more time on this one. I'm going to take this one away now so that we can look at it on the board together. So as you've probably seen, the questions have been ramping up in difficulty here, but the algebra itself hasn't. What we find with number properties questions is that once you see the way into the problem, they're not that hard, which is why it's very difficult to define a difficulty rating for these. If you know the trick, you're in and there's no problem at all. If you don't, you can feel like you're bashing your face off the wall here. Now, in this question, I wouldn't be surprised if you're looking at it going, I'd have no idea where to begin with this. Again, we're still talking about the same things. We're still talking about divisibility, prime factorizing, all the things we've been talking about all through the video. But there's an extra couple of wrinkles in here that have made this more difficult. So let's go pull this apart. Now, the question asked me, which of these 3 options must be integers? Now they've got t divided by something, so I'm going to need to know something about t, but all I've been given to work with is this. S to the 4 is equal to 120 times by t. Might not seem like much to begin with, but let's see what we can do with it. First job, I'm going to go and prime factorize this 120. Now, that is going to be 2 cubed times 3 times 5 times t. Right, so once I've got the prime factors of 120, you might be wondering, well, how does that help? Where is this going? The important clue in this question is that we've got s to the power of 4. We know s is a positive integer. We've taken that positive integer, raised it to the power of 4, and we are told that that is equal to 120 times something. Prime factorized it. S to the power of 4 equals 2 cubed times 3 times 5 times something. Don't know what t is. But what we can say is that each of the prime numbers in this prime factorization must be some multiple of 4 because it's s to the power of 4. And so in prime factorization, there must be 2 to the power of 4 in there somewhere. There must be 3 to the power of 4 in there somewhere, 5 to the power of 4. I don't know how high it goes. It could be 2 to the 4, 2 to the 8, 2 to the 12, 2 to the 16. I don't know. All I know is that the powers of 2 in this prime factorization must be a multiple of 4 because I've got s to the power of 4 here. If that was s cubed, I would say that the powers of 2 must be some multiple of 3. 3, 6, 9, 12, I don't know what they would be, but I would know they're multiples of 3. And we can use that to say that, okay, if the powers of 2 are going to be at least a multiple of 4, then I can say, well, t must have a 2 in it, because the 2 cubed times the 2 in the t would give me 2 to the power of 4. Same with the 3. I've got 1 3. I need 4 at least, so t at least has 3 cubed in it. Same with the 5. I've got 5 to the 1 there. T must have at least 5 cubed in it. And again, there's going to be something on the... I don't know what that is. It might be 1. This might be all that t is, but equally, it might have another batch of 2s, 3s, and 5s in it. At the very least, I can say that t includes this, because s to the power of 4 and all the powers within s must be some multiple of 4. And so I need to bump these up, the ones I know that are in there, at least to some multiple of 4. Well, now I know a lot more about t, and I can go check my options here. So first one, t divided by 2 squared times 3 squared times 5 squared. Well, I've got a 3 cubed and a 5 cubed in it, so that's going to be enough, but I've only got 1 2. So if I divide this by another 2, and we can write this one out just to prove it. So t divided by 2 squared times 3 squared times 5 squared. Again, the 5 squareds are going to cancel. The 3 squareds are going to cancel there. I'd cancel with a 2. I'd be left with a over 2 there. Don't know what a is. Could be 1, could be 2, could be 10, could be 50, could be something else. But again, this question, which of the following must be integers? I don't know. Could be, maybe not. So 1 is not going to work. And now it's the same pattern with the other 2. If for number 2, t divided by 2 times 3 times 5. Well, I've got a 2. I've got 3 3s. I've got 3 5s. I've got more than enough. If I divided t by 2 times 3 times 5, I would at the very least have 3 squared times 5 squared times whatever this a is at the end, this integer a. So that must be an integer. Now this one, okay, we've been thrown a bit of a curveball here with the 15, but I could rewrite that as t over 2 times 15 is going to be 3 times 5. So I've got 3, another 3, 5, another 5. So 2 times 3 squared times 5 squared. Well, in that case, I've got 2 times 3 cubed times 5 cubed within t already. Again, I've got more than enough. If you were to do the division, I would end up with 3 times 5 times a on that top line. A must be an integer. I know that whatever's in 3 must be an integer. So 2 and 3 must be whole numbers. They must be integers, which means our answer to this question is D. So bear in mind that bit about s to the power of 4 here. We were told s must be some integer. So s to the power of 4, when you raise a number to the power of 4, it means that every prime factor within the prime factorization of that integer, the power must be some multiple of 4. 2 to the 4, 2 to the 8, 2 to the 12. I don't know, but I know it must be some multiple of 4. And you can use that as your way into this question. Now, we've said it a couple of times already, but we're about to throw the last question up on the screen. Fair warning, we're ramping the difficulty level up with this one. This will probably be challenging. You don't need to be able to answer this question to get into the mid-40s, even the high 40s, maybe even a 50. You could probably get a 50 even if you're getting this question wrong. So I'm going to throw it up on the screen. It'll be a bit of a challenge. We'll give you a little bit more time than usual to work on this one, and I'll see you back here in a couple of minutes to take a look at it. Okay, as we said before putting this one up, this one's a real challenge. So if you want a bit more time to have a look at this one, feel free to pause the video now. We'll still be here when you get back, but I'll take it away so that we can take a closer look. All right, yeah, just as a caveat, just to emphasize, this is probably one of the hardest questions we've had in one of these videos. So even if you're up there looking for a 48, 49, or a 50 on the quant section, this one, you don't particularly need to get this one, but it's a nice challenge here, and well done to you if you cracked it. If you didn't, let's take a look at the solution, how you might go about approaching this one. So first of all, we've got to decipher a huge amount of text going on here. And so we're told that we've got some hole, and that hole has space for t tables of equal length running along its center. So I've got some kind of great big long hole going on here, and I've got a bunch of tables. All of them are about the same length. Well, no, all of them are exactly the same length. We're told they're the equal length running along its center. We've been told that we need to have a gap between each table of a third the length of each table. So let's begin to turn this text into some algebra. I know I've got t tables. I'm going to need some variable for the length. Now, my mind immediately just goes, let's use L. But L and T are going to get us muddled a little bit because they look so similar, or could get us muddled a bit. So I'm going to go to the next letter. I'm going to use something that looks nothing like a T. I know it sounds a bit strange. I'm going to use M for the length of each table. So I've got a table of length M, a table of length M, a table of length M there, and I need a gap between any two tables of a third the length of each table. So this gap between the tables is a third of M. Same there, that's a third of M. They also require an identical gap between the table and the wall at the end of the room. So an identical gap, same length of gap, between a table and the wall at the end of the room. So a third of M there and a third of M there. So we've got some scenario where we can set up an expression for the length of the room here. Unfortunately, we're told the length of the hole is 296 feet. So we can use that to set up an equation here. So my 296 feet, now that's going to be equal to t tables of length m. So the total length of the tables, all the tables together, is going to be m times t. And then I've got the gaps. Now, in the diagram here, you can see 3 tables and 4 gaps. There will always be one more gap than there are tables. Because if I started from one end, I would go gap table, gap table, gap table. But then I need that extra gap at the end of the room. So that it doesn't matter how many times you extend that pattern on. We know I'll tell you now, there's unlikely to be 3 tables in the room. This is just a diagram I've drawn. But if there were 3 tables, there'd be 4 gaps. If there were 4 tables, there'd be 5 gaps. 5 tables, 6, so on. There is one more table. So t plus 1, that would be the number of gaps times by the length of those gaps, which would be a third of m. So I'm going to take this right-hand side and multiply out the brackets. So a third m t plus a third of m. Now, I can group the m's and the t's together. So I've got 4 over 3 mt plus a third of m. And that all equals 296. Okay, now I'm going to multiply both sides by 3 to get rid of the fractions. But I'm not going to multiply 296 by 3 just yet. And that's going to equal 4mt plus m. And then I can take out the common factor of m there, 4t plus 1. Okay, at this stage, this might not seem very helpful, but what we're going to do with this is I'm going to take this 296 and begin prime factorizing it. So we've got 3 there. That would be 2 times 148, or 2 times 2 times 74, or 2 times 2 times 2 times 37 times 3. So this whole expression is going to be 2 cubed times 3 times 37 is m times 4t plus 1. Now, at this stage, you might be thinking, how does that help me? What have you done there? Why have you bothered doing that? But what we can say here is we've got on the right-hand side, I've got 2 things, an m and a 4t plus 1 in parentheses, and they're multiplied together to give me this left-hand side. Now, the important thing is what's inside the parentheses gives me the clue here, 4t plus 1. So that, whatever that number is going to be 1 more than some multiple of 4. And now I can take a look over on the left-hand side. It can't involve the 2. Because anything with a 2 is going to be an even number, and that will either be a multiple of 4 or 2 bigger or 2 smaller than a multiple of 4. So anything involving the 2 will not be 1 bigger than a multiple of 4, so I can ignore that. My other options are the 3 and the 37. Now, 3 by itself is 1 less than a multiple of 4, so it's not going to be 1 more than a multiple of 4. 37's looking good. That is 1 more than 36, which is a multiple of 4. But I just need to check 3 times 37. Would that be 1 more than a multiple of 4? Well, you could go and do 3 times 37. It's a great big number. And then check, well, what's the nearest multiple of 4 and see if it fits. Or we could say 37 is 1 bigger than a multiple of 4. Well, 3 times 37 would be 3 times bigger than a multiple of 4. So it wouldn't fit with 4t plus 1. So what I can say from this expression is that 4t plus 1, in the way this is set out, 4t plus 1 must equal 37. And m, we were told here, m is the length of the table. The length in feet of each table is an integer. So I can rule out any fractions here. I can rule out any messing around with that. M is going to be 2 cubed times 3. Now, I don't need that. That's irrelevant to the question. But if the question was something different, what's the length of the table, then I'd be able to tell. What I'm interested in is how many tables there are. And as we did there, 4t plus 1 in this expression, that must equal 37. T is the number of tables I've got. So all I need to do is rearrange this to find t. So 4t is 36. T is 9. And that's going to be my answer here. Now, as I said at the start of this question, don't worry if that was a complete mystery to you. This question is a nightmare. This is hard. This is genuinely hard. And even if you're up there at the high 40s, you don't need to get this question right in order to get yourself a 50. But if you can decipher that word soup and convert it into algebra, then you're halfway there. This bit about the bottom with the number properties, about seeing this idea, what's in the parentheses, 1 bigger than a multiple of 4? Well, in this expression, that can only be the 37. If you can reason your way through that, then you're onto a winner with number properties, and you should be able to answer a vast majority of these difficult questions. So that's the end of the first half of our number properties video. As I said, this is about formalizing the things that can be formalized, and we've tried to give you a couple of rules that you can use to break these questions down into something you can use at least some sort of quasi-algebra for. Next time, we're going to look at the ones that are just a real pattern spotting ones. There is very little in the way of formal algebra. This is more about, yeah, as I say, spotting the pattern, seeing where the question goes and working your way through them. There are two sides to number properties, the formal side, that make it up as you go along, and pattern spotting side. And so please come back next time where we'll put the two together. And once you've seen both sides of this, you should have everything you need in your toolbox to be able to go and attack all these number properties questions. All right, I hope that was helpful for you. I hope you found this useful, and we'll hopefully see you back here next time for more number properties questions.